So the final part of the recap that I would like to do about jointly distributed random variables is computing expected values. Right, so if you remember, for continuous random variables x, or even discrete random variables, but doesn't matter. So if you have random variables x, for variable x, the expected value of a function of this random variable, so this turned out to have this very clean expression. So this was integral minus infinity to infinity, let's call it s, of g of s times px of s ds, okay, where this was the probability density function of x. Okay, so this was true for a single random variable x. Okay, so now it turns out a very analogous formula holds for jointly distributed random variables. Okay, so for jointly distributed random variables, x and y, right, so we have the expected value of a function g now of x, y. So this, instead of being the integral, it's now the double integral. So you have double integral s going from minus infinity to infinity, t going from minus infinity to infinity of g of st, and now you have the joint probability density function ds dt. Okay, so this is the exact analog of what we saw for, this is the analog for single random variables. Okay, so now you just have jointly distributed random variables, you have the same thing. Okay, so one very clean formula that you can derive for this, so this we derived in the last class and it's also there in the notes, so I'm not going to derive it now, but a very simple special case of this is that the expected value of x plus y, okay, for any random variables x, y, any x, y, so this turns out to be equal to the expected value of x plus the expected value of y. Okay. These are jointly distributed random variables. So what does it mean, the expected value of x alone? So this just means taking expectation according to the marginal distribution. Remember, the marginal is just, we defined it like this, right? So px, and this just means the marginal for y. Okay, so that's what we have out here. Okay, and this is a very powerful theorem. So this is called the linearity of expectation. And in fact, you can derive a slightly more general version of this. So if you have any constants a and b, so for any constants a, b, they don't have to be bigger than 0, but they are real numbers. So you have ax plus by equals a times the expectation of x plus b times the expectation of y. Okay. And the reason this is very useful is that very often when you are trying to analyze the expected value of random variables, you can break it up into the sum of simpler random variables, some x, y, and so on, and then computing the expected values of those simpler random variables could turn out to be easier. Okay, so we will see some examples of those in your homeworks and such. But this is, for this reason, this is a very useful formula. Now you might ask, does do expressions like this, like the sum of expected value of the sum is the sum of expectations, does it hold for other functions, right? So for instance, is the expected value, is it true that the expected value of a product, right? So is this equal to the expected value of x times the expected value of y, right? So it turns out the answer is no. Okay, so this is not equal in general. So however, this equality holds when x and y are independent. Okay, and this is actually a clean and simple fact to see. Okay, so and it follows from the fact, so this follows from the observation that if x and y are independent, okay, then the joint density function pxy of st, this is simply the product of the marginal density functions s times p y or t. Okay, and you can derive this. So if you remember, this looks very similar to what we have for independent events, right? And it's true for exactly the same reason. Okay, so I'm not going to derive this, but this is a nice fact. And if you apply this into the definition of the expected value of xy, you end up being able to prove this formula. Okay, so anyway, so this so for the products, this is not always true. It's true only when x and y are independent. Okay. But if you are interested in the sum of two random variables, and if you look at their expectation, that is always equal to the expected value of x plus the expected value of y. Okay, so the x and y don't need to be independent. Alright, so this completes the survey of jointly distributed random variables. So these are things that we saw in the last couple of lectures a while ago, so I wanted to recap them. Okay, so next we will move on to a basic introduction of statistics.